This conference will now be recorded.
Okay, so am I audible? Can you hear me? Perfect. Okay, so good evening, everyone, and welcome back to a fresh new session on scorecard development exercise, scorecard development workshop, and when we were working on the logistic regression model. The logistic regression model is one of the very important models which we are going to use for our model develop or scorecard development exercises, right? In this particular workshop, and hence what we started doing was we used a basic data set. We started working with the German bank data set, and from there we started looking into which are the variables that should be kept and all. So we started off with the final model variable selection exercise. So when I talk about the final model development exercise or final model variable selection exercise, so it implies that I'm now in a state where I'm trying to select all the model variables which would be finally used for my model development exercise, right? So this is table one, final model variable selection exercise. Model variables selection. Right. Okay. So this is your second table. Table 2 is the first iteration of this logistic model. Right. So over here, there are a few things that we have seen in the last session. We have seen how is it that these variables can be selected using the stepwise selection. Then we have seen how is it that these variables could be selected using the forward selection, and then we have seen how is it they could be selected using the backward selection process. Now, after doing this, the common set of variables between the three sets, right? So which again and again appeared in each of the three selections were the ones which had been chosen for model development. And over there, what I see is that yes, each of these variables have been sufficient enough, right? So each of the variables have been uh, statistically significant, and they were kind of there was no ambiguity in the signs of the variables, right? So what we'll do is we'll just add a few more columns to this particular table. Now one is ambiguity sign. So I'll call this the sign check. The second is significance check. And the third is contribution check. So over here, what is the first thing? So first of all, I'll see where the sign checks has been passed or not. So for the information, now this is by the intercept. So the intercept says that if none of the variables, so if I do not have any variables in my model, the probability of y1 would be positive, right? And it would be estimated by this intercept value. So as the intercept would increase, the probability y1 would increase. So obviously over here, what I have is a key. Now, when I talk about the check account is the current account behavior, and we have seen that better the current account behavior is, the better is the probability of the borrower. Now, borrower to become a good borrower. So over here in this data set, I'll tell you. So when we look into the dictionary better, we get a better understanding. Checking account variable was is in the form of 0, 1, 2. 0 stands for negative current account balance. 1 stands for positive current account balance, and check account 2 stands for no checking account. So therefore, as the value of the checking account in the category increases, I can see that the probability of the borrower of being a good borrower also increases, right? Then on the other hand, I see that the p-values are also kind of statistically significant. Right. So all these variables are in kind of sync with each other. Right. So that is something that we have seen already. Okay. So there is one more table that I needed to add over here. So one of them, so one of the variables that I have over here is the target variable. So first is y equals to 1. If borrower Okay, so over here what we have is right. So okay, so over here, okay, So I have the target variable over here, the target variable mentioned over here. And basis that target variable, what I have been doing is I have done the variable selection and then I have run the first version of the model. Now I have been checking whether this variable or these the model variables, whether they are appropriate in terms of the signs, or whether their signs are ambiguous or not, whether their signs are statistically significant or not. And what I have checked is that whether they are contributing significantly to the data or not, I mean to the model or not. So what is the most important contribution, which is the variable which has the highest contribution? That is one case that we need to generally check. So over here, one thing that you see is, so checking account is keep. Okay. So or for all the variables, when we look into their signs, we see that yes, they are having the proper sign with the origination risk. So basically, if one of the variables go up or go down, the univariate will move in the opposite direction. Okay. So now the next question that comes out is the statistical significance. So over here, what we have is, okay, so this is on MB. Right. So similarly, statistical significance. Now, statistical significance may what we are looking into p-value. First is insignificant. So when I look into the checking account, the duration, the history, employment, other installment, and installment rate, you see that their p-values are very less, right? So therefore, these are all significant variance. Right. Now we do the contribution check. We now see that how much of the variable, how much of the variables are contributed. Now for the contribution check, we will leave out the intercept over here. So the continue condition check that we will do, or the contribution check that we will do in terms of the world chi-square statistic for the respective variables, right? So this contribution is nothing but the value of the world chi-square statistic over there. Now the next part is that I will take up all the values from this point to this point. Okay. So what I've done is I have looked into the contribution check, right? So one thing is that what is the total amount that the account contributes, right? From its different variables. So one thing you can see is that from the last three variables, the so from the last three variables, one thing that you can see is that the contribution is much lower compared to what the first two variables are. So therefore, in this exercise, one thing that we can clearly conclude from this iteration is that the check account and the distribution distribution of the the distribution of the duration of the loan are two very important, or would be two very key important risky segments if we are actually working on that. Now, the next question that comes out over here is that how do I assess the quantity or the quality that I describe at this level? So, well, what we do over here is now, now if you have a look into this check account, right, you will see that this the Walt chi-square over here is 55, right, and the contribution is 11. So it says that this so it says that out of all the total okay, now if I convert these to percentages, so you will see that 50% of the total contribution comes in from checking account. So current account variables are one of the most key variables when we are describing the or when we are trying to develop an acquisition kind of a model. The loan property is the duration is also very important. So these two taken together, they are explaining around 74% of the total population. Now if you have a look into this, you will see that the installment rate, other installment, etc. So these variables are somewhat, so they are important variables. They are important, they are statistically significant, and everything is fine with them, but their contribution is much lower relative to checking account and duration. So basically, if you look into the contribution that is made by these two variables, one very important thing that you see over here is that there is, like, these two are kind of contributing 74%, and directly then it falls to 8, 6, 5 and 4. So these two variables by far become very important in the behavior, right? Now also another important thing is that other installment and installment rate, right, may be correlated to some extent, because other installments gives us an idea about the fixed obligation that the borrower has. The present installment rate gives us an idea about the the present installment rate gives us an idea about the money or the installment rate which is being paid to that this particular loan is charging. So it looks at the current obligation, right? So in a way they can get associated at some point of time, but however till this point one thing I can clearly see is that these variables are, so these are the ones which has been selected up to this point, right? Now the next question, so these variables are unambiguous, statistically significant, and there is a certain, and they are each of them are contributing. Now let's have a very quick look into, so the next state, the next level of selection filter that we impose is we need to understand whether these independent variables are correlated among themselves. And that is why the next important check that comes out to us is the variance inflation factor check, right? I now need to know that whether the variables are linearly associated amongst themselves or not. So that is whether there is a problem of multicollinearity associated with the variables. So what is multicollinearity between the variables? The multicollinearity between the variables is nothing but it is the linear association of the variables. So what I want to say is, if other installment and installment rate is a is a linear variable of, or they are linearly combined with, let's say, history, right? Then then I should be able to write history variable as a linear combination of other installment and installment rate, right? So then I should be able to write one as the factor of the other, that is one is dependent on the other, and there is no independence. So over there, in such case, we need to ensure that the variable that we are using are independent variable as well. So we require, the model requires variables which are unambiguous, statistically significant, and which are independent, of course, because they will ask you to work with independent uh, variables, right? So when I'm developing scorecards, I need to ensure that the variables themselves or the aspects of the scorecard that they are capturing are absolutely Indian in between them, right? So therefore, uh, what we need to do is we need to ensure that these variables are not linearly dependent on each other. They must be linearly independent, right? Now, having said this, let's look to the next set. So the next set is the variance inflation factor. Now, the variance inflation factor, or the test for multicollinearity, comes from the linear regression exercise. Now, after this exercise, the variables which will have a VIF of more than 2, right? They are the ones which will be eliminated from the data, right? Okay. So this is executing the logistic model. So now the next part that we have over here is assessing the existence of multicollinearity among the explanatory variables. Okay. Assessing the multicollinearity amongst the explanatory variables, right? Okay. So how do we do that? We do this, we generate the multicollinearity from the regression function, from the linear regression function. So the code that it will be, the procedure that we use over here will be the regression procedure, which is procreg. Procreg data. right? So the question that comes out over here is VIF is nothing but the variance inflation factor. So what is the VIF? VIF is nothing but 1 by 1 minus R square of the kth auxiliary regression equation. Regression. So what is an auxiliary regression equation? An auxiliary regression equation is regression equation of one independent variable of the other explanatory variable. So over here, what I'm trying to do is the auxiliary regression equation is nothing but the regression equation of one explanatory variable on the other explanatory variables. Higher the R square, implies for the variable chosen. So now what we'll do is for these variables that we have for which we have developed the model, run this let percent mod bars 1 and we'll run a okay. Now the cutoff of the VIF is the cutoff of the VIF figure is 2. Now VIF for variables which have VIF more than 2, they are removed from the data. But variables which have VIF more than 2, I mean less than 2 are the ones who are retained into the analysis, right? And from where we decide whether to keep or drop them and so on. Okay, so the next part that we have over here is the cutoff of the VIF figure equals to 2. Now over here, now why is this cutoff 2? So if the cutoff is 2, let me put it like this. So, corresponding to a cutoff of 2, corresponding to a cutoff of VIF equals to 2, the R square for the auxiliary regression equation R2 for the auxiliary regression equation will be equal to 0.5. Right? So thus it means that if the VIF is 2, it means corresponding to that the R square of the auxiliary regression equation is 0.5, which means 50% of the variation in that independent variable is being explained by all the other variables, or even more than that is done, then that's a concern. So we generally expect that not more than 50% of the variables must be okay. I'll take up. Okay, so before I move on, so are there any questions? Okay, so over here, if you look into the results, we will see that all the variables have VIF of less than 2, right? So I'll just put this over here. Okay, so I have VIF or the correlation, multicollinearity check. Okay. Right? Okay. So now if you see, you will see that the VIF is also in line and if VIF is less than 2, right? So the cutoff of the VIF is less than 2. So now over here, I'll have the keep drop exercise. I'll take the keep drop decision. So which are the variables to be kept and which are the variables to be dropped. Now kept and dropped in the sense like the variables for the final model, because from here I'll be kind of going to develop the final model. Now when I say final model, so this will be the final model itself. So parameters would not change. Now what we would need in addition to this table is the so we would need the VIFs, and also they will comprise of the final table. Also we would need to have a look into the model accuracy how has the model performed, right? So I need to look into the model's discriminatory capacity. I need to look into the model's case, Gini, the rank ordering of the model, and how has those things happened, right? So with respect to the scores. So does all everything hold good on the development data or not? Now, once that part is done, then what we do is we enter into the validation data, and in the validation data, we do similar checks, right? So over here, so obviously this is drop, this is keep, and all the other variables are. So over here, one thing that you can clearly see is that at this stage, when I have got an iteration of the model, right, I am first looking, even before I go to assess the goodness of fit of the model or where the model is performing. These are the four levels of checks that I need to do in order to understand that do I need to run a second iteration of the model or not, right? So all the values are below VIF is less than 2. So things look good up till here. Now, once this is done and it is finalized, after that, the next set of exercises will initiate. So in the next set of exercises, what we want to do is we want to incorporate other features, right? And we want to look into, we want to understand that how is it that this model's discriminatory capacity. So what exactly do I mean by the model's discriminatory capacity, right? What do I mean by the model's accuracy? So these are some of the important questions that we need to address over here. Similarly, we also need to address questions regarding to cutoffs, the cutoff that we have had seen in the past and so on. So there are a lot of different questions. Now, once this part is done, right? Once I have identified, the number of, so once I've identified the model and everything. So now what we need to do is we need to first of all score the file, right? We need to get a scored file, and the rest of the checks will be done on the scored data. Right now, one very important thing is that at an unsegmented level, if a certain result is holding, then no matter which way you do a segmentation, right? So you should get more or less the same pattern result. So you must get more or less the similar results. So so you need to assess the robustness of the model along those lines. So one by one, we will be kind of performing these checks, right? Now let's go to the next part. So let's run the logistic regression model once again. Now, what we are doing is we are running the model, right? So we have identified the variable. We have seen that yes, these are the variables now, right? So over here we are now executing a final version of the model. So this is where the final version of the model. The development. So it will be nothing but the same model that we have kind of done over here as well. The set of variables remain the same. It doesn't get unchanged. I mean, they remain the same, and therefore we run the model over here. Okay. Now this is where the model results are. I was using stepwise selection. I have the odds ratio estimate, and I have the association of predicted probabilities and observed responses. Now, this table gives you an idea about the overall performance of your model. So it gives you an idea about the discriminatory capacity of your model. But before that, there are a few things that we would like to identify. One is C table. This is an important option. Then you have the LACFET option, right? Then you have P equals to, then you have output out equals to segmented Okay, so this is the full-fledged, or this is a more comprehensive code that is written in logistic regression mode. I mean, you have other options as well, but what we do is we generally use this particular code. In the over here, what am I trying to do? I'm trying to develop the model, not only develop the model, I'm trying to look into classification table. I'm trying to look into the residual operating characteristics. I will come to that. I'm looking into the lag fit option. So I'm looking into the overall fit of the model. So that this is where through the lag fit option, I'll be taking the Hoffman-Lemaitre test, right? And and when I develop the model, one thing that I could clearly see is that the model is statistically very significant. So that is obviously one very big advantage with us. So all those are now on the other hand, we would also want to see the whether the overall fit of the model was good. Right. So let's run this code and let's see the output. And from there, we'll kind of move ahead. Right. So now we'll run this code and we'll see the different output that comes out over here. That comes out over here. We'll take up each of those tables and we'll start explaining as to how and why each of these tables, they kind of fit together. Okay. So let's run this. So let the code run. I'll just be back. Okay. Okay, so before I move on, there is a question from Shashank. I'll take this question. So Shashank asks, can you please repeat again, how do we decide the unambiguous sign check? Okay, so basically, Shashank, what we do is from the model, so when we ran the model, right, we got a sign of the coefficient, right? We with the coefficient, we got an attached sign. Now, if we have that sign, now we know that there is a business logic to that, right? So now that logic and the sign must coincide. So let's say, for example, duration. We know that the greater the duration for which a particular person applies the loan for, the lower, the lower is his affordability, right? Because otherwise, the higher his affordability would be, what he would do is he would ideally just very quickly pay up the loan. So because he cannot pay up the loan that quickly, that is why he's looking for a longer term. And the higher this applied duration period is, the higher are the chances of the borrower being bad. Therefore, the probability of the borrower being good has negative sign or is negatively related to the duration variable. So higher the duration of an applicant, lower are his chances of being a good borrower, and hence duration is a very important variable. And you can see that the sign is negative, and that is also what the business requires, business says, and therefore you say that, okay, yes, this variable has a unambiguous sign. Now, if something was opposite to what the business intuition was, let's say other installment, I know that the higher the number of other installments are, what it means is that higher is the fixed obligation of the borrower, right? And lower are his chances of being a good borrower. Now, if that had a positive association with the probability of being good, right, which is our target variable over here, so then that would have been a major concern, right? So therefore, what we are kind of seeing is that other installment has a negative relationship with the good borrower, and hence we would say that, okay, this borrower is something like, okay, this borrower is a good borrower, and then we would say that, fine, so the sign is in line with what the business in with the intuition is, and therefore we would say the variable has an unambiguous sign. Now, if it was counterintuitive, then we would say it's an unambiguous, it's an ambiguous or a counterintuitive sign, right? Great.
Tell me, how did we check it for check account?
Sorry.
This check account is current accounts or the first variable.
Yeah. So the current account variable has three categories in the data. It has a category 0, it has a category 1, and it has a category 2, right? So 0 stands for overdrawn balances, 1 stands for accounts which have positive balances, and 2 stands for accounts who do not have current account. So basically, it is seen that accounts. So as you move from 0 to 2, right, your bad rate gradually falls. So it means the chances, the number of good borrowers gradually increase, and hence your probability of being a good borrower increases. Therefore, with the categories of checking account, it this model, the target variable has a positive relationship. So what we can see is that with this current account variable, right, there is a positive association with the probability of being good. So as an account, current account category of the borrower increases, means he becomes a better and a better borrower, and hence his chances of being a good borrower increases. So that is why, checking account has a positive sign. Yeah. Great. Great. So from here, I get to see the keep drop facility, and I see that none of the variables are kept back. So this is for the timing. This is what my model iteration is. However, Now that this model, so this is the model iteration, this is the model that I have with me. However, does I need to understand that how is this model performing, right? I want to understand, we need to understand the nitty-gritties of the performance of this model, which is very important. So therefore, now let us see what are the other tables which has been generated as a part of this exercise. Now, as a part of this exercise, a very important thing which has been generated over here is the scored file. So over here you see that I have created a data set, model development unsegmented score, with a value pred underscore y underscore 1. So if you see over here, you will see that there are 703 observations and 27 variables. Right. Now, previously, when the data set was kind of, so if you look into the initial data set, so there were 703 observations and 26 variables. So now what I have is I have 27 variables, right? In this data set, model development, unsegmented, scored data. Now it is these code files which will be the most important thing, and it is this code. Now it is this core which will help me understand that how is it that the model is performing. So is the model performing in a, how accurately is the model performing, right? At a decile level, we look into the accuracy of the model. At an overall level, we look into the accuracy of the model, right? And then at the decile level, at the segment level, so we will try to assess the what should I say? We would try to assess the overall behavior of the model, right? And we need to validate that the model has been correctly developed. So that is something that we need to talk about. Okay, so let's have a first look into the scored data. So the data set that I have over here is the model dev unsegmented unsexplored data file. Now the first thing that I want to do over here is I want to understand that how many goods or how many bads are there and how is it that the score is. So first of all, I want to know that how is it across the score decide is this particular account or is this particular accounts performing, right? So first of all, what I need to do is I need to divide this score data into 10 equal parts. That is, I need to create the score deciles, right? And for each of the score deciles, what we need to do is we need to compute the number of goods and the number of bads. But before doing that, right, now we have a response value, right, which is uh, so we have the response, right, which is a 1 or a 0 kind of an account. If the account is a 1, the probabilities of score should be relatively higher. If the probability or if this is lower, I mean 0, so then the probability of being good will be much lower. So basically, if I do a proc means and I kind of look into the probability estimate, I should see a very stark distinction between the two indifference rates, right? So from here, what we need to do is we need to look into we need to decide the scores and we need to generate all the descriptive measures for required for the model validation exercises. Right? But before that, I need to find out that through my model that I have developed, how many has been identified as one and how many zeros, and how many has been correctly identified as one and zeros. And before that, I need to know whether, so how is it that the overall goodness of fit of my model is looking like with this particular model, given that it has not been healed over the, so how good or how bad this particular model is performing, right, compared to the original ranking of one and zeros. So this is something that we are going to first of all look into, right? Okay, so so first of all, let us look into uh, the overall goodness of fit of a logistic regression model. So in the model that we created, right, we looked into the original. So we looked into the kind of, we looked into the statistical significance of the individual regression coefficients, and we saw that yes, they are pretty working fine, right? So they are, uh, there is a statistical significance. Now comes the next part. We need to understand that whether the actual and the expected distribution has been currently statistically significant or not. Now, if that has been done, then you can say that yes, the overall fit of the model is also very good. That is, the difference between the differences that you get to see between the actual and the expected figures is actually not very high, right? And what we need to do is we need to show this for both the good and the bad responses, right? So this is where, the third table or the third test actually comes in, which is the test for overall goodness of fit of the model, which is called the Hosmer-Lemeshoff test, right? So the table after this is the Hosmer-Lemeshoff test table. So with this variable, the way this variable has been kept, right, you have the actual frequencies in each of the score deciles, right, and you have the observed number of goods and you have the observed number of bads. So you have the expected number of goods and you have the expected number of bads. So one thing that you need to check is that the observed and the expected responses must be very different, must not be very different from each other, both for, for this both for the response one and response zero. So the two distribution must be very close to each other, right? So over here we do have a set of records, right? Now with this, we also look into the model's discriminatory capabilities. We will actually look into as to exactly how is it that the model's discriminatory capacity is identified, right? And we, given that, we will talk about how to calculate Gini, how is Gini calculated. Also, we'll talk about KS. We'll talk about the difference between Gini and KS, and we'll also talk about the importance of the rank ordering process and how is it that the three of them together gives us an idea about exactly how the model is performing in terms of its discriminatory capacity and in terms of its stationarity and accuracy. So these are the three fields in terms of which we need to identify. But before we go into this part, one of the important things that we need to talk about is the overall goodness, or the overall goodness of it test, right? Which is provided by the Hosmer-Lemeshoff test, right? So, so the third table that I will create over here. Now, the Hosmer-Lemeshoff tests, there is a specific Hosmer-Lemeshoff test statistic, right? Which I do not recollect at this point of time. I'll have to look up that formula, right? But I'll give you an idea about how exactly this test has happened. So this test has actually happened in the way, your selection equals to stepwise was happening. So over here we are trying to assess whether at the overall level, how significant are the residuals? Are the overall residuals significant in nature? So over here the residual is nothing but the difference between the observed and the expected figure, right? So what we generally try to do is we try to identify the expected figures, and then what we do is we check whether the difference between these two is statistically significant or not. Right. So let's have a quick look into that. Now, at the overall level, right, by an intuitive method, if we can show that the residual is not significant, then and if you can count and if you can kind of reconcile that to the results that is shown in the Hosmer-Lemma test, then we can say that yes, at the overall level there is no major difference, and the overall fit of the model is quite good, right? So up till now, what we looked into was the individual regression. So we will look into the so what do you call this? You call your individual statistical significance, right? Now you are looking into the overall statistical significance. So this is individual goodness of it. So this is goodness of fit, the variable level at the regressor level, right? So goodness of fit at the regressor level. Now we are going to look into the goodness of fit at the overall level. Okay. Okay. So this is group. I'll call this deciles. So I'll call this the deciles. Right. So what are deciles? Deciles is when you divide your data into 10 equal parts. Such that each of the groups have your 10% of the observations. So over here you have response 46 bads and 24 goods. Now one thing you can clearly see is that as as you're moving on the deciles for decile 1 to decile 10, right? You can see that your number of bads are gradually declining. So there is so a very simple way to check for this is the bads. Right? So there are certain breaks in the rank ordering over here as well. This shows that your model that you built is not a perfect model. So till now there was more or less something, right? It was kind of going down. Now at 17 there is a major break, and then you kind of go down. And over here also. But the number of bats over here are very less. So That will not be a problem. But there are rank ordering breaks, and we'll come to that. Okay. Okay, so now let's have a very quick recapitulation over here. Now what I'll do is I will plot the actual and the observed, right? The observed versus expected for response 1, and then observed versus expected for response 0.
May
Yeah, tell me.
here in expect we are getting values in decimal. So our
Right.
model gives the y equals to 1. I mean,
No, the expected these expected values you do get expected values in decimals because it is being generated from the Hausmann-Lemaître's test statistic, right? So this is just for comparison. It does not mean that if you have 20.98, you cannot have like 20.98 records in a decile. That is actually 21. Now these figures are kind of reported to two places of decimals because they are expected figures. Right now, if you let's say you're using a chi-square statistic to calculate the frequency, the expected frequency count, right? So then let the PSR and chi-square statistic, you do get them in frequencies, right? But these expected figures, so this is the actual work observed versus expected comparison that you are doing. But when you are looking into, like say the discriminatory capacity, you are looking into the your your stability issues, etc., etc. Over there, you are using the observed outcomes. You are not using the expected outcomes anywhere. This expected outcome is just to check whether the model that has been fitted, right, is like has explained the residuals on the overall app properly or not. So is it that the residuals that remain, the difference between that remain, is it statistically significant or not? If it is statistically significant, then you know we need to rebuild the model, right? So this expected figure that you are seeing over here can be in decimal because it is an outcome of a mathematical calculation, right? But you
yeah.
do not use these figures anywhere, so it does not impact the general applicability or the general implementation of the model or the use of the model.
Mm-hmm.
So whenever you are trying to assess that discriminatory capacity, the accuracy, you will finally, based on your scores, based on your PT score, whatever you have, you create a 1-0 flag. The moment you will create a 1-0 flag and you will do the counts and everything, you will always get whole figures. You will never get decimals. So these decimals are there because it's calculated from a mathematical statistic, which is the Hausmann-Lemaître test statistic. And I'm just comparing that whether these differences that between these two is significant or not. It is just for this analytical exercise. It does not impact any of the applied part of your business model, of your business problem. Right? Any other questions on this, Richard? Anything that you're confused about?
No, no, got it.
Okay, fine. I'll just check the chat box. I have a query over there. Ah. So if you look into this graph, right, if you look into this graph, very simplistically, you just look into this graph, nothing, right? So like nothing as such. So you just look into this graph, you will see that both the distributions, that the histogram of both the distributions are more or less close to what your, I mean, your expected figures are actually very close to what those observed figures are, right? So, so one thing that you can clearly say is that there is not much of a difference between these two, right? Now, if you want to do it in another way, so there's another way possible. So what you do is you take the difference between the observed and the expected whole square, and then when you divide it by total number of t sides, you should get a value which is something very close to zero. Then we'll say that there is no statistically significant difference between each of them. Okay. So like over here, so you have for one of the graphs over here, right? So similarly, this is your response one, observed versus expected. It is the count of accounts. And this is t sides. Right. So this is one of the graphs. Now, similarly, if you do it for response equal to zero, you should get a similar graph. have response 0. Observed. Response 0 expected. Which is your response 0 observed versus expected. The next part that I have over here is the count of. Okay. So now you have the count of account for both. And one thing that you can see is that for both of them, one thing that can be seen is that they are, I mean, the bands, they are very, the two distributions are very close to each other, right? So the null hypothesis that observed distribution is nothing significantly different from the expected distribution is it's true, right? The null hypothesis is accepted at alpha level of significance. So that means if the null hypothesis is accepted, it means the p-value should be greater than 0.05. So now let's have a look into this. You can see the chi-square figure is 0.5863, 5893, so which shows that the value is greater than 0.05, and then hence I can say that yes, what the kind of plot that I saw through the graph and the example that I show over here are very similar, right? So the results shown by the graphs and the results shown by statistical tests are similar, right? So I can say that okay, things are in kind of line with what the output is. So this is the Hosmer-Lemmershor test table. So what does the Hosmer-Lemmershor do? The Hosmer-Lemmershor test is the F statistic counterpart of linear regression. So in a linear regression model, what do? In a linear regression model, you use the Hosmer-Lemmershor, I mean, you use the F test to assess for the statistical significance, right? And over here, what are you doing? I mean, the overall goodness of fit of the model, And in this, and here, what are you doing? Over here, what you are doing is you are kind of so you are kind of doing this for purpose response 1 and 0, right? And what you are trying to see is that whether so you use the Hausmann-Lemma test to identify the overall goodness of fit in a model where the dependent variable is categorical in nature, right? Now, on the other hand, now F statistic or the F test was for the continuous counterpart. Now that the categorical counterpart of that table is the Hausmann-Lemma goodness of fit test table. And what I can see is what the table says over here. The same thing or a similar concept is also kind of shown by the Hausmann-Lemma test table. So one thing I can clearly say over here is that yes, the goodness of fit of this model is pretty high. The decile distribution of the overall scores for assessing the overall fit of the model of the developed, right? So this is what the decile. So this is from where I get the initial decile distribution, right? And now I have the Hausmann-Lemma test, and I can clearly say that yes, the overall fit of the model is good. So first we selected the variable, we got the variable, we ran the model. There we did 4 levels of checks, right? So what were the 4 levels of checks that we had done over here? First is sign check, significance check, contribution check, VIF check. After that, we have looked into the overall fit of the model. How does the model look on the whole, right? After that, what you do is now you look into the overall discriminatory capacity of the model, and you go ahead to look into the accuracy of the model, right? So the question that comes out is how is it that we would look into the accuracy, the discriminatory capacity of the model, and that is shown in the next tab, right? Okay. So for this, okay, so any questions up to this point? Okay. Now, this Excel sheet is an Excel sheet which computes three very important concept, three very important things for the model, right? Or and both and all of them are related to the in assessing the overall fit of the model, how good or how bad the model fits the data, right? So first, what it does is it calculates the Gini, right? The Gini, the case, and the rank order, right? Now, if any of these are not there, right, so that will be identified in these graphs, right? And also what it does is it takes the results which are generated from the from the SAS reports, and it compares the figures that this table generates and the one that SAS generates. So that has been used to benchmark the results that we have obtained in this Excel sheet, right? So this is unsegmented model path. I will call this, sorry, the logistic regression model performance. Okay, so let me explain this. So in this table, so we get the number of observations. We have the observed response, and we have the for response equal to 1 and for response equal to 0, right? And from each of these numbers, we have the entire, kind of the decile distribution that is there. So we put the numbers over here, right? Now for each of the deciles, the observed bats come in here, the observed goods come in here, okay, and we compute the bat rate. So the bat rate is nothing but the relative distribution of the bat. So what it believes is, so if your segments rank order, more or less the bat rate should gradually decline without any jump in between. Now, for computing the discriminatory capacity, I need to understand the cumulative. So we need to look into the cumulative bad rates and the cumulative good rates, right? Now for computing Gini, we need to look into the difference between the cumulative good and the bad, right? Also, I need to look into the cumulative bad of the ith value and cumulative bad of the I minus 1th value. So this will give us the margin, right? So over here you have, so these are used to, and all these figures, they are needed for Gini. So first let me show you through the table that how is the Gini appearing and how do I interpret the Gini. Then we'll go back and we will talk about how is Gini calculated, how is Gini constructed, and so on, right? So what exactly does Gini does, and how is it that it is easy for us to calculate that and so on. Okay, fine. Okay. And when you are actually comparing your model, the discriminatory capacity of model, so there must always be a line of randomness. And so first let's try to see how this works, and then we'll see, then we'll deep dive into each of this column of this table, right? So, first of all, over here, the two basic measures that we repeat are KH and Gini, right? Now, what happens is that if this is a validation data, right? Out of time validation data. Then we would also capture, then we would also look into the deterioration of the deterioration of the case and the gene. So we'll also look into that as well. So there are many of these things that we need to look into. Right. So for the time being, what we are looking into is the case, the gene, and the rank order. Now these three will kind of tell you. So one thing I have seen is all my variables are statistically significant. Second, I have seen is that the overall fit of the model is good.
Now what I want to see is that can my model appropriately discriminate? Now, if the rank ordering is not satisfied at one bucket, even at one score bucket, right? And if that percentage break is sufficiently high, right? That's more than 10%, then your model has to be generated. So what it means is that there is some variable which I have used in my model description, which is creating this problem, right? So then you need to identify out a way through which you can actually rectify your models, right? Okay, so let's have a quick look into this. So we'll use the records that we had from there. And from the SAS report that we had, we will also bring in these results. We will talk about what it means to analyze this association between the observed responses and the predicted probabilities. So we will talk about that as well, right? So there are multiple things that we need to talk about. So let's have a quick look. So I will take this entire table to the next page. I'll take the observed values. I have the response 1. I have the observed over here. And I'll remove this table from. So I'll just select this. So now the question that comes out here is so I have the observed good in my D size, and I have the observed bad in my D size, and over here I have the total number of records, right? 210. The observed number of bats. Okay. So now what you have over here is you have the automated sheet, right? So all the figures, all the input got calculated, right? And from here, what you have is your case and your Gini is also calculated. So what is case? Case is your Konrad-Smirnov test measure. And over here, one thing that you can see is that there is a line which is coming, and there are cases where there are multiple breaks. So on the whole, the trend is a downward trend, no doubt. But in between, at multiple score parts, right, your discriminatory capacity of the model is not really very unique. So even though on the whole, your good and bad is getting properly distinguished, right? But at each decile level, at each decile, within some deciles, there are certain major issues. Now let's say, for example, what is the percentage of like rank ordering break over here? So from here 20, so you can see 46, 43, 31, 21, and then suddenly you have 22. Now 21 and 22 are very close, right? So what it means is, so this is the one that I was saying, right? So as the discriminatory capacity of your model falls, right, or if your model is unable to discriminate at certain stages, the number of bats placed in each of the two segments is very close to each other. Whereas the bats placed here between these two buckets was very clear. But somewhere in the middle parts where the average profiles are very average, right? So that's where your accounts are kind of start losing the capability, right? So this will be something very typical of the overall accepts approach as well when we go to go over there, because some of the so in the fifth decile is what, so fifth decile is more or less your median, right? So that's where your median probabilities or middlemost probabilities lie. So the average profiles lie in fifth and the sixth deciles. Right now, again, as you go ahead to 7, 8, 9, 10 decide, so they are the words of records. So you get very, I mean, they're the best records. So what you get to see is the number of bads are very low over there, and the number of goods are very good. So at this stage, right, when the model is placing the records, right, if I remove this, not not keep any colors over here. So one thing that you can clearly see is that over here in this middle bucket, right, the placement is very close by, right, 49, 48, 21, 22. So there is a minor break. Again, 14 and 17. So it means that in these median buckets, the middle buckets, right? So who are the middle buckets? The middle buckets are your marginal accepts and your marginal rejects. So these are the marginal accepts, right? Not marginal rejects, but marginal accepts, because they have the median buckets and all. So 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 they are not the marginal accept. I mean, they're the very median kind of profile, the average kind of profiles. So this model, the way we have actually used the variables, right? This model is unable to predict or is unable to classify between the good and the bad when the profiles are average, or when the PD, the probability to default is at near around zero point 0.5, zero point 0.6 or something like that. So around 0.5, 0.6 and so on. So at that probability level, it is this particular person can, or this model is unable to kind of rank the borrowers in the order of the in the are unable to rank order their borrower in terms of their risk, right? So there are certain issues, and at a very high level, what happens is the number of rejects are very small, right? So the number of rejects is very small. So I mean, sorry, the number of bad accounts are very small. So therefore, what happens is the number of goods in this data is very high. So at the upper stages, right, you would actually not see much of a break in terms of the goods, but the number of bads becomes so less that there can be a rank ordering break. So even this rank ordering break is not something that we are concerned about, because this is because of very low number of bats over here. So it means that at the high score, besides it is absolutely correctly discriminating between the good and the bad borrowers. So the goods are, I mean, they have the credit, bads are bads, but at the I mean the number of bads are very less, and means there can be some kind of a issues in this discrepancy. So basically the differences is very less. But if you have a look between 14 and 70, that is 6th and the 7th side, right? The 6th and the 7th side, this break is a major break. So 21 to 22 is something which should not be there, that can be easily fixed. But this fall 14 to 70, right? So what it means over here is in the 7 cell there is relatively more number of borrowers, so it is unable to distinguish in the profiles, right? So they are not, the scores in this bucket is not rank order, but on the whole, if you see, the overall discriminatory capacity of the model is good, and hence the Gini is also pretty high. So I think the Gini is around 54, right? Yeah, so a model Gini of 0.54 in this respect is a pretty good score. So on the whole, you can see a negatively sloping trend, but in between, the model uses out this capability to distinguish between good and bad. So what it means is that this model that we have developed in this way that we have developed, or the the, so all the variables are taking everything together. There may be some issues in some variable which is causing the problem, which we could not detect at that level, and hence we need to deep dive and we need to see what is causing that lack of discriminatory capacity at the 6th and the 7th itself. Right? Any questions up to this point? Okay. So up to this point, is the idea clear? Any questions?
And I'm not getting one thing.
Yeah.
Suppose we have an overall count of 703, okay? So it
Mhm.
might be the 200 or 150 out of 700 profiles are almost same or similar in nature.
Sorry.
It
Once
can,
again.
suppose I have total count of 703, right? I have divided it
Uh-huh.
into the 10 deciles. So
Uh-huh.
suppose I have say 150 profiles which are almost similar in nature in terms of the behavioral and the attributes or the independent variables. So in that case, I mean, uh,
No, where do I have 150 accounts which are similar in behavior?
no, I'm not saying we have. We might have, right?
Hmm.
If I have
Okay.
700, I might have a family 150 accounts which are same, almost same profile. Okay. So
Uh,
like I have divided the buckets, 10% buckets. So suppose I
uh,
have some 20% of the data which has almost similar profile. So in that case, how will I be able to, just divide or discriminate every 10% of the profile? In that case, my two deciles can have very similar percentage of the bad rate. If my 20% of the population is very similar in terms of its profile. I mean, you're getting, I mean, what?
No, I'm unable to just frame the question in my mind. Can you just come
Uh,
once again? So I got to that point where you are saying like you have 150 profiles which are very similar to each other. Okay,
okay.
fair enough
Suppose
then.
in 100% of the data, some 25% of my profiles are all very similar. Okay. Now, when
Okay.
I am dividing my 100% data into the deciles, okay, so I will have 10 proportions. So if my
Okay.
25% population or the sample
So
population
if
is
you
all,
are if in that case, what happens often is if your profiles are very similar and that the range of a certain value is very high in terms of, so you have say a large chunk of records lying between 0.58 and let's say 0.28 and 0.36, right? So in
Mhm.
such a case, all those 20 records will go in one single decide. So in that case, you will have 9 divisions, not 10.
Okay. And the model should be able to categorize that or discriminate that, right? That is our expectation.
Yeah, so I did because see if you have now the point over here is if you have a look into the number of bats the way that they just placed, right? So now you
Mm-hmm.
need to look into the profiles of these borrowers. Now there is an exhaustive profiling analysis has to be done to see why this 6 and 7 cannot discriminate.
Mm-hmm.
That is always one, right?
Mm-hmm.
Now the next the next part over here is that it may be because that it's not because of the profiles, it's because of the variables. So first what you do is you check whether there are any issues with the variables, right? If you do not find any issues with the variables, then you check with your profiles, because it is either because the profiles are very similar that your model cannot discriminate, or is it because there is a variable which cannot discriminate between the different profiles in the 2D sites.
Yeah, correct.
Right? So you
Yeah.
have to check both ways that which is the way this is happening. Is it happening for like so is it happening for similar profiles, or is it happening because your model cannot discriminate between the extent of heterogeneity which is there? Now see, it is very difficult to say that exactly 50 profiles are exactly the same, 150 profiles are similar. Now there will be certain differences, right? There will be certain differences in there, no matter how similar you want the profiles to be, but there will always be certain differences in some factor or the other. So let's take an example like this, right? So let's say uh, these 150 people who have taken the loan or has taken the loan, they are all MX employees, right? And all of them are into analytics, and all of them are managers in the manager profiles, and they have been working for 10 years, right? That means what their salary bands are also more or less similar. So in terms of income, in terms of their monthly expenditures and everything, they are similar, right? But some of them are Delhiites and some of them they have come from other states. So that means some of them who have come from other states, right? They have their, so they are either rented or they are mortgage, or they have a mortgage going on. Whereas the people who are from Delhi will have their own house. So obviously this is a big, this becomes a big discriminator in the kind of risk, because with if a guy giving everything else remaining unchanged, a guy who has a mortgage is always relatively more riskier than a guy who has his own house. That's where your risk
Mhm.
differentiation will come in. So no matter how similar you want to do it, right? There will at least be one or two variables which are very different,
Mm.
which distinguishes them, right? Because it's very difficult to have such But if so, no matter what, no matter how similar your profiles are, your model should be able to discriminate it as less risky and more risky between any two profiles. So given any two profiles,
No matter how similar they are, your model should have the capacity to distinguish, assign a higher probability to one and a lower probability to one. Right? So it should ideally do that.
Okay. Yeah.
Right?
Yeah. Then.
But what you said makes sense, because there are cases where we do get such cases, where one decile has relatively higher concentration and then one of the decile is not present there. So let's say instead of 10, it has been divided into 9.
So on
So
the
you
basis.
do get such cases. It's not that you don't get it.
Yeah. So basically, the model is creating decides on the basis of the similar ranking and the similarity of the bad rates.
I didn't get you.
Like basically, the model is
Can you once
creating the
again?
deciles or the groups on the basis of its bad rate, right? I mean, the center point is this
The
only.
predicate value. So it is creating the profiling that, I mean, the deciling that you are doing it as per the predicted probability that you have,
Bad
right?
rate, yeah.
And once you have created the decile, within each decile you are looking into the number of observed goods and the observed price,
Yeah, yeah, thanks.
right? Okay. Okay, fine. So one thing that we can clearly see from here after this exercise has been done is that so one thing that we have clearly seen from here is that how is it that that this how is it that the overall goodness of fit of a logistic regression is determined, right? So once that is something that we have seen. Now from there comes the next question, that how do you assess, how do you know that the figure that you have generated in this Excel sheet is correct? So I need to benchmark these results against something, right? So I I benchmark these results against that table, which shows the relationship between the association between the observed responses and predicted probabilities. So when we are working, when we talk about discriminatory capacity, what we are trying to do is we are trying to analyze the association between observed responses and the predicted probabilities. Right. So what is this table between observed responses and predicted probabilities? So if you look into the raw data, right, so there are some records which are 1 and then there are some records which are 0, right? Now, if my model was 100% accurate model, what would it do? It would assign the highest probabilities to 1 and then the lowest probabilities to 0, right? And there would be an accurate classification of good and bad. However, my model is not very accurate, right? I mean, there are certain imperfections because this is a supervised model that we are learning over here. So what what I need to understand, how good or how bad the model kind of how good or how bad the model would kind of be, right? What we need to do is we need to look into the association between the observed probabilities and the predicted and the observed responses and predicted probabilities. So over here, one of the most important parts are these parts. So these three pairs that we talk about, one of them is called the concordant pair, right? The other is called the discordant pair, and the third is called the tied pair. Now, if your model can work in three ways. Number one, it can appropriately perform relative risk ordering. Second is inappropriately relative risk ordering, right? And third is indifferent relative risk ordering. So it can perform the functions in any one of the three ways, right? Now, this, so over here, now over here, now let's see, so what exactly are concordant? So there are three kinds of pairs. Now, when a model is able to, is performing appropriate relative risk ordering, it is called concordant pairs, right? So it is called concordant pairs. Now, what happens in a concordant pair? Now, see, there are two possible outcomes, y equal to 1, which is good, and bad. Now, ideally, if my model is performing correctly or appropriately, it will always assign a higher probability to y equals to 1. So, so a borrower who is a good borrower will always get a higher probability because he has a better profile compared to the other. Now, similarly, a borrower who is y equal to 0 will always get a lower probability because this borrower is a bad borrower and they have and it has a relatively worse of profile. So basically, profiles which have, you know, so borrowers which have, higher, so so if I make out certain 1-0 pairs, right, I will see that accounts which have higher probability and is y equal to 1, right, and so basically like if I make out 1-0 pairs, if I start making out 1-0 pairs, then I should get some pairs where a y equals to 1 has a higher probability than a y equal to 0. Similarly, I can get pairs where y equal to 1 has been assigned a lower probability than y equal to 0. And there I can get pairs where y equals to 1 has the same probability as y equal to 0. So I can look into the three different pairs, right? So these three different pairs will give me three different ideas. So over here, the the pairs where y equals to 1 has a higher probability than y equals to 0, right, is treated as a concordant pair because this is where the relative risk ordering has been appropriately done. The discordant pairs are the ones where inappropriate relative risk ordering has been done. That is, the good borrowers have been given lower score and the bad borrowers have been given higher score. And tied pairs are the ones where the same probability has been assigned to both. So now the model's discriminatory capacity is identified through the percent concordance or the percentage of the concordant pair as the total number out of the total number of pairs, right? So this is where the total number of concordant pairs are there divided by the total number of pairs. Similarly, percent discordance and tied pairs are the part which shows the lack of inaccuracy. It is because the higher the percent discordant and the percent tied will be there in your data, in your model, right, lower will be the discriminatory capacity of your model. So higher the percent concordance in your data, higher will be the discriminatory capacity. So the percent concordance being higher means that the number of pairs that are being created, they always have higher number of concordant pairs. That is, more and more account has been appropriately risk ordered. So from here, I get the table. So this table summarizes certain key measures, the SOMASD, the gamma, tau A, and the C statistic, which summarize or which will help you get a sneak peek into the total number of into the overall discriminatory capacity, right? So if we have a look into this, so if I come across, Alt EAV. So over here, one thing that you can see is, so I will link this. Okay. So now, if you have a look into the figure that I have over here for Somers D and the figure that I have for the Gini over here, sorry, I made the change in the wrong table. Mhm. Huh? Right. So, okay. So over here, one thing that you can see is the Gini that I have obtained as a result of this exercise is 0.54. And the Gini that I have obtained over here in terms of Somers D, sorry, the Somers D that I've obtained here is also 0.54 rounded up to two places. Now, interestingly, if you would do something like this, 2 into C minus 1, you will get 0.536, which is the Somers D, or which is the Gini. So basically, what comes out over here is that that each of these measures, right? So each of these measures, be your Somers D, gamma, Somers D, C, or and Gini, I mean Somers D or C, both are your approximations of Gini, right? In some cases, you may see that you have so in some cases you can see that the Gini is there, right? So Gini is measured. In some cases, you may see that the director report the Somers D or they report the C statistic as well. So the C is Somers D is a direct approximation of Gini, and the C statistic is 2 into C minus 1 is equal to Gini. So you get Gini from there. So this is something that we need to understand, right? So, so this is the way we benchmark the results. So one thing that I can clearly see from here is that on the whole, the model discriminatory capacity is good, but the model cannot discriminate between the good and the bad in these core decides, right? Now, it may be the reason that it cannot discriminate because there are some issues with the variables themselves. So the variables are not kind of correctly. So each of these variables that we have, right, are not. What should I say? So they are not. So some of them may not be appropriately rank ordering in nature, and because of which that rank ordering is impacting over there. So the next step is to assess the ranks and plots, the rank ordering and the plots of these continuous variables, of these model variables, and to check whether these model variables are kind of rank ordering or not. Now, if they do not rank order, then it is because of the fact that they are not rank ordering, that is why your model is not working fine, else it would have worked fine. So there you need to fix the rank ordering issue by comparing the rank ordering of the variable, or if the variable is not rank ordering correctly over here, then you need to look into the profiles, right? If that is the if profiles are the case, then you may need to reshuffle, you need to go back and readdress your sampling problem. So the way you need to fix a particular problem would depend on, so basically it would depend on the way the problem actually arises, right? So that is the next part of this discussion, right? So now you need to understand that how to fix a typical rank ordering problem which can arise on the development data. So first we'll fix this on the development data, and then we'll try to analyze that how is the model performing on the validation data. Now, variables which may have certain issues, right, will be something that would be something that we would need to take care of in the next sections, right? So that is the discussion that we have tomorrow. That how do we fix the rank ordering issues and improve the discriminatory capacity of the model, and how do we do an accuracy analysis for a logistic regression model on the development data. So those are the two questions that we address in tomorrow's discussion, right? So any questions up to this point? First, I'll take that, and then we can close for the day.
Tanmay, I have again one question.
Yeah,
Like,
yeah,
how
yeah.
did
Please
we
tell.
get this
Please tell.
number? So 0.37. How did we get this number or the Gini like 0.54?
Okay, the calculation of Gini. So the calculation of Gini is something I'll show you tomorrow, right?
Okay.
And and the C statistics, see, basically the way it happens is, if you have a look into this, the percent concordance is 76.7, right? So
Mm-hmm.
from there, the C statistic is 0.678. Now, the C statistic is the outcome of the sensitivity and 1 minus specificity. That's the ROC curve. We need to talk about that as well, because we'll use the ROC curve to derive the ROC components to derive the your accuracy in the model, right? So we decide to use a cutoff. From that cutoff, we'll get our estimated one and zeros, and then we'll see the accuracy of the development sample. So from the C, once you have the C statistics, so 2 into C minus 1 is your Somers-D, which is 0.537.
Mm-hmm.
And the exact Gini calculation that I have done, if you want, what you can do is you can click on this cell. So you can see the actual formula that has been used. So it will direct you to the cell. So this sheet is an absolutely automated sheet. So basically, as your figures change, right, you will see your issues also. I mean, all your figures and all your graphs are also changing. So you can
Mm-hmm.
look up this formula, right? So
Mm-hmm.
tomorrow we'll talk about that, and then what I'll do is I'll sit down and I'll walk you through all each and every formula for these model discriminatory capacity, accuracy, and all. But first, let's look into the applied part. Then we'll come to talk about the descriptive or the theoretical.
Okay. And this these pairs, okay, right, like where the probability are given as accurate or inappropriate or the same probability has been given. So these we have calculated on the overall data, right? Not on the deciles level. Like it is like the concordant pairs and the
No, no, no,
discordant pair
no. This is on the whole development data.
development
We are
data,
counting
right?
the total number of pairs that is possible in this data set.
Mm-hmm. Mm-hmm. Yeah, okay.
So how many random pairs you can pull out of this data?
Mm-hmm.
Hmm.
Okay.
Right? Okay.
Yeah.
So let's take a pause here for the day. I have downloaded your respective recordings for this workshop that we've been doing. So today is day 6, right? So after this, I'll have 6 recordings, and I'm sharing this Excel sheet with you now, and the one that I've been discussing till now. So these two Excel sheets I'm sharing with you. You can go through it in the meanwhile, and the code sheet while I'll upload the recordings of the day. Right? Okay. So thank you guys. Thank you for your time, and let's catch up tomorrow. Thank you.
Thank you.